and if I pass current through this coil, what will happen? If I pass current through this coil, what will happen? You are going to get some flux that is being produced in the coil. Okay, some flux is being produced in the coil. Okay, now, if you bring another coil, and keep it in the influence of this, flux. Okay, keep the other coil in the influence of the first coil flux. Then if you connect a voltmeter across this, okay, then you can find some voltage is being induced in this coil. So that voltage which is induced in this coil is because of this flux linking with these conductors. So what we have to say? Flux linking with, we have to write like this, flux linking with the conductors. So what we are doing, we are trying to link the flux with conductors. When flux links or cuts the conductor, okay, an EMF is induced. An EMF. What is EMF? Electromotive force, which we call voltage, is induced. So where this EMF is induced? Induced in the coil. Induced. So where this EMF is induced? EMF is induced inside this coil. Okay. This is written, or this statement is given according to Faraday laws. According to Faraday's laws of electromagnetic induction. So according to Faraday's laws of electromagnetic induction, okay, Faraday law of induction. So what this Faraday's law is telling? Faraday's law tells that whenever a conductor cuts the flux, EMF is induced in the conductor. And the rate of EMF induced, E, is proportional to the rate of change of flux. Rate of change is generally written as d phi by dt. What is this d phi by dt? D phi by dt is nothing but rate of change of flux. So the EMF induced in the conductors, because of this flux linking with these conductors, is proportional to the rate at which this flux is linking with these conductors. That is given by this equation. Okay. So by this equation, what you are going to conclude, that whenever you bring a conductor and if you make the conductors cut this flux, or flux cutting the conductors, then EMF is induced in the conductor, and that EMF is proportional to the rate at which this flux is being linking with the conductors. The rate at which d phi by dt is nothing but it is the rate. Generally, we call it as rate of change of flux with respect to time. Suppose your flux is in this like this, then this is your flux and this is your time. The flux is varying with respect to time. Okay. So the EMF induced in the conductor will depend upon the rate at which this flux is varying. Now, see here in this what we have done? We have brought a conductor 2. Suppose this is a conductor 1 or coil 1 and it is coil 2. Okay. The coil 1 and coil 2 are brought nearer and the medium by which this flux is traveling to this coil 2 is air. Air is the medium between these two coils. Air is the medium between these two coils. What I can do is, I can make a iron piece. I can make one iron piece act as a magnet by 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 wounding a wire on this on this wounding a wire on this iron piece. And if you pass some current into this coil, then this bar iron piece will act as a magnet. So north and south poles will be created on the magnet. Why these north and south poles are created? Because this coil when current is passed into the coil, flux of lines will start flowing from the coil. Now what we are doing, we are keeping a iron piece which is a ferromagnetic material, and what it is doing, the entire flux which is created inside the conductors of the coil is now traveling through this iron piece. Okay, is traveling through this iron piece, and now this iron piece is acting as a path. Now the iron is acting as a path. Okay, for what? For the flux. Generally, flux is represented with phi. So the iron is acting as a path for the flux. Suppose if you have an iron and a air as the path for the flux, definitely the flux will take iron. Okay, iron path. The flux will take iron path because iron will have low reluctance compared to air. Okay, compared to air, since iron has the low reluctance. Okay, so the flux of lines will tend to move in the iron path only. Now what I will do is, instead of manufacturing a iron piece in a solid structure, I will manufacture the iron piece like this. Okay, I will take a rectangular shape. Okay, so this is your iron piece. Inside it is hollow. So this is iron. Now I have made this made up of iron. This material is this, and this I am calling it as a core. The name I am giving it to is core. Okay. Now. So this is your core. So what is the principle I am going to use? I am going to use the same principle. When wire is wound on this iron piece, now the flux will travel in the iron piece only. Because why? Because the iron piece will give the path, and it is having low reluctance compared to air. Now what I am doing, I am wounding some wire on the core which I have manufactured with the help of iron. So this is your winding or coil. So I have wound one coil, and what I am going to do is I am going to send the current I into this coil. Then what will happen? According to Faraday's laws of electromagnetic induction, or when current is passed through the coil, what will happen? Flux will be produced. That flux which is created inside the coil, now will not go into the air. It will complete its path. It completes its path through the core. So this is the path of the flux. Okay, this is the path of the flux. That means the flux is now completing its path through like this. Suppose it is created and it is from A to B to C and to D and to A. That is, the flux is now path is completed. So what I am trying to say is here, the flux is now confined to your metal or core. Okay, metal or core. So now what I am trying to do is I am trying to wound a winding on this other side of the core. Okay, other side of the core. So if I wound a winding on the other side of the core, okay. So what I am trying to do, I am trying to wound a winding on the other side of the core. Now, according to Faraday's laws of electromagnetic induction, what is happening? What is happening? So I have told you in the first slide. So when flux is cutting these conductors, EMF is induced. EMF is induced according to Faraday's laws of electromagnetic induction. EMF is induced according to Faraday's laws of electromagnetic induction. So this flux phi is coming like this, and it is cutting the conductors on this other limb. Let this I will call it as primary winding. This I will call it as primary winding, and this I will call it as a secondary winding. Secondary winding. Okay, secondary winding. So when current is given to the primary winding, a flux is set up, and that flux is linking with the conductors on the secondary. So according to Faraday's laws of electromagnetic induction, okay, according to Faraday's law, okay, according to Faraday's law, so what should happen? What should happen? An EMF should induce, should, okay, should induce in the secondary winding, okay, secondary winding. That means now E2, capital E2 is the EMF induced in the secondary winding. Okay, IP is the primary current which you have sent into the primary, okay, primary side of the winding, and E2 is the EMF induced in the secondary side. Now let us take IS is the secondary current. If you connect a load across this, what will happen? If you connect a load across this, okay, then what will happen? The current IS will flowing into like this. Okay, now the primary voltage is, let us take it as VP. Okay, so the primary voltage is VP, the second primary current is IP, the secondary induced voltage is E2, and let the terminal voltage is VS. Let the terminal voltage between this phase and neutral is VS. Okay, VS, and IS is the secondary current. So I have how many parameters? VP. VP is called primary or the voltage given to this source voltage or primary voltage. IP is called primary current. Okay, primary current. Okay, and it is called primary voltage. On primary side, how many parameters are there? Two parameters. One is voltage, primary voltage, and primary current. On the secondary side, I have E2. E2 is called secondary induced voltage. Secondary side induced voltage. Okay, induced voltage. What is VS? Secondary side terminal voltage. Okay, terminal voltage. Okay. And what is the remaining parameter? Remaining parameter is 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 called secondary current is called secondary current. Secondary current. Okay. Now let N1 is the number of turns on the primary side, or NP. NP is the number of turns on the primary side, and NS is the number of turns on the secondary side. Okay. So NP and NS. NP and NS. What is NP? NP is the number of turns that we have wound on the primary side, and NS is the number of turns we have wound on the secondary side. So these are the few parameters which you have to remember while dealing with principle of operation of the single phase transformer. So for what I have done, I have taken one core and I have wound some winding on the primary side, and I have given some voltage so that the current flows into this primary winding and the flux is set up by the primary winding. So this flux will take the path of the iron piece or core. Iron piece or core. So this is called core. This entire iron piece is called core. And this is called limb. This is called limb. And this is called other limb. So it has two limbs. Okay. So this path is provided by the iron piece and it will link with the NS number of conductors. NS, where NS is the number of turns. Okay. So NS number of conductors on the secondary side, and E2 is induced in the secondary side winding according to Faraday's law. Okay. Now if you connect a load, then IS is the current that is drawn from this E2 winding, and this current will go into this load, and Vs is the voltage across this load. Voltage across this load. Okay. Now let us take the same core. Okay. Same core and wind the winding. What winding which I am winding is the winding which I am winding is called primary winding. Okay. And another winding is called secondary winding. So what is the voltage which you have to give to this primary winding? The voltage which you have to give is VP, where VP is called primary voltage, where VP is the primary voltage which you are giving. Now, what is the current that is flowing in this? Is called IP. Okay. Now, what is the power that we have given to this primary side power? So the primary side power is primary side power is how much? VP into IP. VP into IP. VP is the voltage and IP is the current given to this transformer. So that power is what it is doing. The power which we have given, that is primary power. Okay, the power which is an electrical quantity, okay, is converted into flux. What is flux? Is flux a electrical quantity or magnetic quantity? It is the entire energy which you are given to the primary side is converted into flux. Can anyone tell me what is flux? Is it electrical quantity or magnetic quantity? So
magnetic quantities.
Yeah, the flux phi is magnetic. Okay, so magnetic field. It is converted into a magnetic field. Okay, magnetic field. Now on the secondary side, what you are doing? You are again winding some wounding. Okay, and this is the winding which you wound on the secondary side with N2 number of turns. The number of turns is N2. Okay, with N2 number of turns you are winding on the secondary side. Okay. Now this flux links with these conductors and EMF E2 is induced, right? EMF E2 is induced. Suppose if you connect the load as if in the previous slide, then IS will start flowing into this load, and VS is the power. Sorry, VS is the terminal voltage. VS is the terminal voltage. Now, what is this VS into IS? VS is into IS is the secondary power. Okay, secondary side power or output power. Is input anukunte, then this will be output. So this is secondary side power. Okay, secondary side power. Okay. So what you have done, see here, if you observe carefully, the electrical power is converted into magnetic field, and from magnetic field, and it is again converted into electrical. VSIS is electrical again. Okay, electrical. So what you have done here, the electricity or electrical power is converted into magnetic field, and magnetic field is again converted into electrical field, electrical energy. So magnetic field or magnetic energy. Okay, so if you consider this as energy, okay, this is energy, okay, power, and this is also energy. So electrical energy is converted into magnetic, and magnetic is again converted into electrical. So this transformer is called, so the transformer is called electromagnetic conversion device. Okay, electromagnetic conversion device. Why I am calling it as electromagnetic conversion device? Because the electrical energy is converted into magnetic energy, and again magnetic energy is converted into electrical energy. So this transformer, I can call it as a electromagnetic conversion device. So this is one point. This is the second point. Okay, and third point is, according to energy law, energy neither be created nor can be destroyed. So energy which you are giving to the transformer, which I call it as input energy. Okay, input energy is equal to the output energy, but we cannot destroy. Okay, cannot destroy energy. Okay, so the input energy should be equal to the output energy for a constant time. If the time is constant or same, okay, for input and output, so I can call it as input power. Instead of energy, I can call it as input power is equal to output power. Input power is equal to output power. Because time is for the same time, we are supplying the input and output. So the energy that is spent on this, the energy given to this input is same as the energy that we are consuming for the same time period. So energy is nothing but power into time, right? E is equal to power into time. If time is constant on both sides, TT gets cancelled, and input power should be equal to output power. Then what is input power? Input power is Vp into Ip. Okay, Vp into Ip, which is equal to Vs into Is. Vs into Is. Okay. So the input energy is equal to output energy. Okay, input power is equal to output power. Okay, that means power is not changed in the transformer. We can't change the power in a transformer. But what we are doing here actually is, let if Vp is equal to 100 volts, okay, 100 volts, and the power which we are sending is, and the power P which you are sending is, okay, 100 watts, 100 watts. Okay, then find, then if I want to find Vs and Is, Vs and Is, then this relationship will help us. This relationship will help us. So P is equal to, P is equal to Vp Ip. Vp is 100. So P is 100. So 100 is equal to 100 into Ip. Ip is, now I am going to calculate. So from this Ip is equal to how much? 1 ampere. Ip is 1 ampere. Okay. And so Vp Ip is 100 into 1. 100 into 1. Okay. And is equal to now let Vs is 50 volts, that Vs is 50 volts is equal to Vs into Is. Vs into Is. So Is is equal to how much? 2 amperes. Is is 2 amperes. That means what is happening? If I give 1 ampere to the primary side, if I give 1 ampere to the primary side, on the secondary side, how much current is coming? So this is your transformer 4. Okay, this is the transformer 4. And to this transformer core, okay, I have the primary winding. I have the primary winding with N1 number of turns, and I have secondary winding with N2 number of turns. Now what I have done, I have given 100 volts to this input, and I expected 50 volts as the output, and the current that is supplied is 1 ampere, and the current which I have obtained on the secondary side is 2 amperes. Is is equal to 2 amperes. Okay, 2 amperes. Ip is equal to 1 ampere. Then what is happening here? When the voltage is being reduced from primary to secondary side, okay, from primary to secondary side, what we are trying, voltage is reduced. If voltage is reduced, then what is happening? Vp to Vs is reduced. Ip to Is is increased. Ip to Is is increased. Okay, Ip to Is is increased, but the power remained same. But the power remained same. Power remained same. Same power, but what is happening here? When voltage is being decreased, the current is being increased. Then this type of connection is called step down transformer. Okay, step down transformer. Why I am calling it a step down transformer? With respect to voltage, I have to tell this step down or step up. Okay, why I am calling it a step down transformer? From 100 volts to 50 volts, it is getting reduced. So I call it as a step down transformer. So if I want to write the step up transformer, then what will happen? If I want to tell it as a step up transformer, okay, so the primary side should have the less voltage. Okay, suppose this is 50 volts. Okay, and suppose this is 100 volts. 100 volts. Okay, 100 volts. Then I can call it as a step up transformer. Step up transformer. So there are two types of transformers. Okay, one is step up and another is step down. If the primary voltage is greater than secondary voltage, then it is called step down. Okay, step down transformer. If Vp is less than Vs, then it is step up transformer. This is step up transformer. Now, so if this is the situation, okay, what happens if Vp is reduced, right? If Vp is reduced, Ip will increase. That means if Ip is less than Is, if Ip is less than Is, then it is called step up transformer. Sorry, step down transformer. Step down transformer. Okay, if Ip is greater than Is, if Ip is greater than Is, then it is called step up transformer. So in step down transformer, what is happening? In step down transformer, what is happening? Step down transformer, Vp is greater than Vs and Ip is less than Is. Okay. So reverse will happen for voltage and current. If voltage is getting increased, obviously the current will get reduced. Okay. In order to, for what purpose this is happening? This is happening because to maintain the power constant. Okay. Power in a circuit. The power transferred from primary to secondary is constant. To maintain the constant power, okay, the voltage and current are getting increased and decreased based on the voltage levels. So then if I want to define the transformer, if I want to define a transformer, then what should I do? What should I write? So if I ask you to define transformer, so a transformer is a static device. Why it is static? Static device because it won't rotate or it will move. It won't move. Okay, it is a static device which transfers power from one circuit to other circuit. So here what is the two circuits, primary and secondary winding. So one circuit to other circuit. Okay, other circuit. Okay. Without electrical contact, without electrical contact. Okay, without electrical contact. Okay, contact. So if you observe, the primary and secondary windings are not having any electrical contact. So even though there is no electrical contact between this primary and secondary winding, we could able to transfer the energy from primary side to secondary side. So a transformer is a static device which transfers power from one circuit to the other circuit. This one circuit is nothing but your primary winding. Okay, primary winding. The power which is given to the primary winding is sent to the secondary winding without a contact, without electrical contact. But using మనం ఏం యూజ్ చేసాం, what you have used to transfer this power? By using magnetic field, but using magnetic field. So electrical contact లేదు కాబట్టి we are using magnetic field and without changing the frequency. This point is very important. without changing the frequency of what? Frequency f. Without changing the frequency. I'm telling without changing the frequency of what? Then you should ask me what is that transferred from primary to secondary? Voltage is transferred, okay, and current is transferred. Okay, both voltage and current are being transferred from primary side to secondary side. Primary side to secondary side. So this is secondary side. So the voltage will have some frequency f. Okay, the input, the voltage, the sending side Vs will have some frequency f, and Is will have some frequency f. Okay, and the output voltages Vs and Is will also have frequency f and f. Okay, now see here in this 4 parameters, the f from primary side to secondary side, the same f is continued. That means f is not changed. Frequency is not changed. Frequency is not changed. Okay. So this is the definition of the transformer. This is the definition of the transformer. So what we have learned till now? So a transformer is a static device and it works on the Faraday's laws of electromagnetic induction. So it works on the principle of Faraday's laws of electromagnetic induction. So I'm writing again the formula which we have derived. Okay. So what is the formula which we have derived? Vp Ip is equal to Vs Is. Okay. Vs Is. Now if I bring this to here, Vp by Vs is equal to Ip by Is. Ip by Is, which is equal to some K, which is equal to some K. That means Vp is equal to, from this what we can write, Vp is equal to K times Vs. Similarly, Ip is equal to, sorry, here what will happen? This will become Is, this will become Ip. So Ip is equal to Is divided by K. Is divided by K. Okay. I will call this K as transformation constant. This is transformation. This is called transformation constant. Okay. So I'm calling this K as transformation constant. Okay. Till now, do you have any doubts? Till now, do you have any doubts? So let us continue the class. See here, when I take a core and I want some winding on the core and some winding on the primary side. Okay. So when I give current to this primary side, what is happening? When I give current to this primary side, what is happening? When I start flowing current on this primary side, some flux is created, and the same flux which is created on the primary side is linking with the secondary side winding. Let N1 is the number of turns or Np is the number of turns. Okay, number of turns on the primary side. And similarly, on the secondary side winding, let I wound it for N2 number of turns or NS. That is the NS. So NS is not equal to NP. NS is not equal to NP. Okay. NS is not equal to NP. Okay. Then when I connect the load, IS is coming from this winding. See here that IP is traveling in this NP number of turns, right? IP is traveling in the NP number of times, and IS is flowing in this NS number of turns. NS number of turns. Then I will define one term called MMF, which is called magnetomotive force. Magnetomotive force. Magnetomotive force. See here, since the flux remained constant, okay, the flux remained constant flux. The magnetomotive force which is developed on the primary side should be equal to the magnetomotive force on the secondary side. For what purpose? To maintain the flux constant. If I don't maintain the flux constant in this winding, what will happen? Some flux will, suppose if you created 100 lines, these 100 lines of flux will come and has to link with this. Suppose some lines are missing. Okay, then what will happen? What will happen? The EMF induced E2 will reduce. E2 will reduce. And this E2 will influence Vs. That means the terminal voltage will reduce. Okay, so this should not happen in the transformer. Okay, that's why you have to maintain the flux constant in a transformer. So in order to make that MMF flux constant, the MMF on the primary side and MMF on the secondary side should be constant. Should be same. Should be same. So the MMF produced on the, what is the formula for MMF produced on the primary side is the current that is flowing in these turns, that is IP, into the number of turns, So this is NP. Similarly, what is the MMF that is produced on the secondary side? The current that is flowing in the N2 number of turns into the number of turns is NS. Now, from this, what is IP by IS? What is IP by S? IP by S is equal to IP by S is equal to IP by S is equal to NS by NP. NS by NP. NS by NP. Okay. IP by S is equal to NS by NP. So we know that IP by S is equal to VS by VP, or IS by IP is equal to IS by IP is equal to IS by IP is equal to, from this equation, VP by VS, VP by VS. So what is IS by IP? From this, NP by NS. NP by NS, which is equal to K. Is equal to K. So what is K? K is nothing but your transformation constant. Why I called it as a transformation constant? Why I called it as a transformation constant? So suppose VP is equal to K times Vs. K times Vs. Okay. So that means if you multiply the transformation constant to Vs, we are going to get the primary side quantity. Okay. If you multiply the transformation constant with secondary side quantities, you are going to get primary side quantity. See here in this equation, I have multiplied the secondary side quantity with a K, then I got primary side quantity.